with the need of low warehouse staff volumes and more space-efficient floor plans, ASRS is more important than ever. With the utilization of machine-to-machine communication and Industry 4.0, our goal was to produce a product that is cost-effective and easily manufacturing scalable.
Now, speaking of manufacturing, we followed design for manufacturing and assembly processes for our product. We ensured that the number of components were kept low and modular, which helped in reducing assembly time. The other criteria were design for cost and design for reliability. These were implemented by using 3D printing process and off-the-shelf standardized components.
Our components are categorized into two main subsystems, electrical and structural. Inside here we have our SoC that is Raspberry Pi 4, which is interfacing with our RFID module and microcontroller, and Arduino makeup with RAM's 1.4 shield that's controlling 3 NEMA 17 stepper motors. This is all powered by 12 volt DC power supply. For the structure, this design is using 2040 aluminum extrusions and L channels for the rack structure. Moving on to the manufacturing process, we use 3D printing for manufacturing our custom pellet system and mounting components. PLA and ABS were our filament of choice. The shuttle system utilizes a belt-driven pulley system for X, Y, and Z axis. The bins utilizes RFID-enabled cards that automizes the storing process. This all comes together to work in harmony using Python and C++.
Since our project is machine-to-machine communication, we had to come with a strong software system that to control our motors and sensor. Therefore, we used robotic operation system, ROS, that for developing the top layers of the software that is responsible about any part in the software system. Therefore, we used publisher and the subscriber feature that is provided by ROS that make each code written by C++ or Python to communicate through topics. Since we had 3 degrees of freedom, we used and modified an accessible library to control our motors and make them work in harmony. In order to achieve the machine-to-machine communication system, we used RFID software program to help the network devices to read the data and make the decision, which make the machine-to-machine application translate the data and can trigger pre-programmed automated action. Now I will demonstrate what I have described and to see it in action. All I have to do is to place this box and it will automatically identify it and store it. Now I will show you how to retrieve an item by using the graphics user interface in this program. All I have to do is click Retrieval and it chooses the item that I want to retrieve, for example G4, and the robot will do it by itself.
It can handle a payload of 350 grams and has a throughput about 1 item per minute.
Also, these all were achieved by $720, which was only about half of the estimated budget.
This was a great feat of engineering. With the flexibility and modularity of our system, future teams will be able to add more features and capabilities such as AI, IoT, and much more. The possibilities are endless. Thank you for your time, and we'd be happy to answer any questions. Goodbye, stay safe, and stay healthy.